Hello everyone. So in this video we will discuss about two-way slab. As we discussed previous video, what is the introduction about the slab, then what is the one-way slab and related design we will discuss. Now in this video we will go to the two-way slab. So what is meant by two-way slab means, first of all, the slab is supported all the four edges, we call it as a two-way slab. Then the long span L suffix Y, then shorter span L suffix L, which is less than 2, we can call it as two-way slab. So RC slab are supported to on the four edges, we call it as a two-way slab. So for the two-way slab, the moments developed in the slab depends on following conditions. Number 1, depends upon the shorter span length and as well as the longer span length. So this is the longer span, this is the shorter span. So depends upon the length, the moment developed will be vary. Then edge conditions. So the edges are supported, either it is a free or it may be a fixed or it may be continuous. So depends upon the edge conditions at the support. Then third one, magnitude and types of load. If in case the load is concentrated load, or so like that, concentrated load like that, or UDL or universally varied load like that, the moment developed will be vary. So as per the IS 456 page number 39, what the code record is, for slab spanning in two direction, we have to consider shorter span. Shorter of the two spans should be used for calculating the L by D ratio. So L by D ratio, for the calculation of L, we have to use shorter span. That is, we have to use L suffix X. So we have to note down this point. Then second one, for the two-way slab, for the length of 3.5 meter, if Lx equal to 3.5 meter, if Lx is equal to 3.5 meter and the loading is up to 3 kilonewton per meter square, 3 kilonewton per meter square, we have to consider the span by depth ratio for simply supported beam. In case if you are using mild steel, we have to apply L by D ratio equal to 35. In case HYSD bars, we have to the factors 0.8 times of that value, 35. In case if you are designing the continuous slab, for the mild steel it is 40, or in case if you are using HYSD bars, 0.8 times of 40. So these are the notes we have to note down before going to design of two-way slabs. The third one, for the shorter span or longer span, moment developed will be vary, as we said earlier. So it is available in page number 90 and 91 in your IS 456, which is explained in the Annex D. So Annex D, IS 456, page number 90. First condition, restrained slabs. Second condition is simply supported slabs. So most of the cases we are going to design simply supported slabs. So in the simply supported slabs, they provided the two table number 26, bending moment coefficient for rectangular panel supported on four sides with provision for torsion at corners. So this is the table which is having a alpha x and alpha y value, depends upon the Ly by Lx. Depends upon the Ly by Lx, there is a value is there. Then we have to refer the table. Here table number 27, they provided for the right angle simply supported four sides of slab. In here also we have to consider this in case of you are going for a simply supported slabs. The formula for Mx, M moment about x axis, alpha x into W into Lx square, whereas moment about y axis, which is equal to alpha y into W into Lx square, whereas alpha x alpha y value only we have to refer from the table. So kindly note it down, page number 90 and 91, Annex D, slab spanning in two direction, which is available in your IS 456. So we have to go through before going to design of slabs. So these are the following requirements we need to know. Let's see design a two-way slab problem. So what are the data is given? That is the first we have to write it. Then only we will get the clear idea. So what are the data is given? The size of the slab is given. That is 3.5 meter into 4.5 meter. So second condition is very very important with these discontinuous edges. Whether edges is continuous or it is discontinuous. That is the first condition we have to note it down. Then simply supported edges. So all the supports are supported by the simply supported. Then we have to prevent the corner from the lifting. So we have to provide torsion reinforcement for the edges. Then only we can easily prevent the lifting when we are loading on the slabs. Then what are the loads they provided? Given live load is given 4 kN per meter square. Floor finish load is given 0.6 kN per meter square is given. Then materials concrete M20 grade of concrete, then steel Fe415 HYSD bars. So these are the given data for the design of two-way slabs. So first of all we need to check whether it is a one-way slab or two-way slab. So for the two-way slab we need to identify Ly by Lx which should be less than 2, whether it is comes or not. So Ly which is equal to 4.5 meter, then Lx which is equal to 3.5 meter, so equal to which is provided, which is given by 1.28 which is less than 2. So we can confirm that our given data is two-way slab. Then we need to calculate the depth of slab. So what are the data is given as per the loading 3 kN per meter square. So based upon the loading we have to refer the IS 456 page number 39. We need to go to the IS 456. Take the page number 39. They provided here the note number 2. So here they provided up to 3.5 meter, up to 3 kN per meter square only we have to use it. But here our load is exceeds 3 kN per meter square. So we need to take it as span by depth is equal to 25. Span by depth we need to take 25. So from the ratio we can calculate the depth, that is effective depth D. So span by 25. So span is, so where two-way slab we have to use always for shorter span length. Yes, shorter span length is 3.5 meter. As per the requirement provided in the IS 456 we have to apply 3.5 meter. So 3500 divided by 25 which is 140 mm for the depth of effective depth of the slab. So we need provide 10 mm at least simple for the slab, then 20 mm cover. So we have to calculate overall depth is 165 mm. From the ratio we have to get the clear idea about the depth of slab. Then effective span. So here they provided the clear span only. So we have to directly calculate the effective span. L is equal to clear span plus effective depth. So your clear span is 3.5 meter, effective depth is 140 mm. So convert in terms of meter 0.14. So L is equal to 3.64 meter. Step number 5, load calculation. So the load combination is here dead load, live load, floor load. So dead load we have to calculate the overall depth 0.165 mm of meter into 1 meter. We always design for 1 meter. Then unit weight of RCC is 25 kN per meter square. So we will get the 4.125 kN per meter. Then live load which is provided in the given data 4 kN per meter square into 1 meter. Then floor finish load 0.6 kN per meter square into 1 meter. So total load, this is we call this a W. So total load is 8.725 kN per meter. Whereas we need to find out the ultimate moment. So we need to find multiply of factor of safety 1.5 into 8.725 which is equal to 13.08 kN per meter. So this is our ultimate load which is acting on the slab. Next we need to find out the bending moment and shear force. So bending moment and shear force, in order to find the that we have to refer page number 91. Table number 26. Read out moment coefficient, that is alpha, for Ly by Lx. Our question is 4.5 divided by 3.5, which is equal to 1.28. So for the 1.28 only, we need to refer page number 91. Page number 91, table number 26, we need to refer bending moment coefficient for rectangular panel supported in 4 sides. So our question is 4 sides, and also we need to provide torsion reinforcement. So table number 26 only we need to refer. In this we having a 9 condition, 9 name is there. First one, interior panels. Number 2, one short edge continuous. Number 3, one long edge discontinuous. 2 adjacent edges discontinuous. But in our question they provided the 4 edges discontinuous. So ninth one, 4 edges discontinuous. So from the Ly by Lx, alpha x is equal to 0.077. So we need to interpolate. Exact value is not provided in the graph. We need to interpolate. Then we find out the alpha x equal to 0.077, whereas alpha y value is 0.56. So from the IS 456 we got the value of alpha x and alpha y value. Now the moment formula is alpha x, moment about x axis, alpha x into WU into Lx square. So 0.077 into our ultimate load 13.08. Then effective span, we need to here substitute effective span 3.64 square. So 13.24 kilonewton meter. Whereas moment about y axis, alpha y WU into Lx square. So 0.056 into 13.08 into 3.64 square, which is equal to 9.70 kilonewton meter. So which is maximum moment along the x axis only 13.24 kilonewton meter is acting. Along the y axis 9.70. So for that, next we need to calculate the shear force. WL by 2, 13.08 into 3.64 divided by 2, 23.8 kilonewton. So we need to check whether we provided the depth 140 mm is sufficient or not. So we need to take maximum moment 13.24 only. We need to consider 0.13 FCK BD square. So we need to calculate we need to find the D. So square root of 13.24 into 10 to the power of 6 maximum divided by 0.138, 20. Here B is 1000 mm. So 69.5 mm only enough to provide the effective depth, but we provided the 140 mm. So almost double the time. So hence effective depth what we provided is sufficient to resist ultimate moment. So our ultimate moment is 13.24. For the ultimate moment 69.5 mm is enough for the effective depth, but we provided the 140 mm. So which is more than enough. Step number 8, reinforcement. So we have here 2 set of moment. So we have to calculate the shorter span and as well as the longer span. So for the shorter span, we have to apply the moment which is got from the along the x direction, that is 13.34 into 10 to the power of 6. Then apply the formula 0.87 into Fy is 415, AST into effective depth is 140. So 1 minus AST into 415, FCK 20, B is 1000, B is 140. We got 980 mm square. So we need to provide the reinforcement for this AST for the shorter span. So we have to provide at least 10 mm dia bar. So adopt 10 mm dia bar at 250 mm center to center spacing in shorter span. We already discussed in the one-way slab. That's why we shortly we provided the spacing, everything. So we need to calculate the how it comes to 250 mm. So then we go for a longer span. So same here, shorter span also we used 10 mm dia bar. So we go for a longer span. So already one 10 mm dia bar is provided. So along over the reinforcement we provided here. So we need to deduct that 10 mm dia bar. So using 10 mm dia bar in the longer span, we need to effective depth 140 minus 10. That already provided the 10 mm dia bar. So here 130 mm we need to reduce it. So here moment along the y direction 9.7 into 10 to the power of 6, which is equal to 0.87 into that formula. So that we substitute here. So here effective depth is 130 mm. So that is only the difference. So AST here 213 mm square. So we need to provide at least 10 mm dia bar. So 10 mm dia bar, at we can provide the manage the spacing. We will provide the longer spacing 300 mm. Maximum spacing is 300 mm. Center to center support in longer span direction. So here 980 mm square. Here 213 mm square. Next, reinforcement for the edge. So these are the edges we need to provide the reinforcement. So at least we need to sufficiently 0.12% of overall cross section. So 0.12 divided by 100. So 1000 into overall depth 165. So we got 198 mm square. So 10 mm dia bar we provided the maximum spacing is 300 mm. Center to center we need to provide the extra reinforcement for edge strips because of support is there, that's why we need to provide that. Then step number 10, shear stress, we need to compare tau v and as well as the tau c. So if it is tau v is greater than the tau c, means we need to provide design the reinforcement. In case tau c is greater than tau v, we need not to design it. We simply provide the at least a 10 mm dia bar, minimum reinforcement bar. So considering shorter span and unit width of the slab, because we always design for the two-way slab, is shorter span we consider. So VU by BD, tau V is VU by BD. So VU is 23.8 mm into 10 to the power of 3. So this 10 to the power of 3 is converting from kilonewton to Newton. So 1000 into 140. So we will get the 0.17 Newton per mm square. Next we need to find the tau C. So for that tau C we need to refer table number 19, page number 73. So PT value, percentage of tensile reinforcement 100 AST by BD. 100 into that shorter span. So shorter span we provide 10 mm dia bar. For that AST value is 315. So 315 1000 into 140, so which is 0.225. So for that we need to refer table number 19 for the 0.225 M20 grade of concrete. We will get the 0.31 Newton per mm square. So for the two-way slab we need to apply the simply supported slab, we need to find the conversion factor, that is modification factor, so which is provided in the page number 72. Page number 72. So page number 72, 40.2.11. In this there is a table is there, overall depth, then K. If we are applying 300 overall depth, D is, so K value is 1. 275, K value is 1.05. So 175 is 1.25, 150 or less than is 1.3. So we here interpolated, we find the value of 1.27. So 1.27 into 0.31, which is equal to 0.39 Newton per mm square. So K into tau C greater than tau V value. So hence shear stress is safe. So tau C is greater than tau V means the shear stress is safe within the permissible limit. So step number 11, to prevent the lifting, all the four edges we need to provide extra reinforcement to prevent the lift. So for that we need to calculate the area of torsion steel at each of corners in 4 layers. So formula is 0.75 times of AST. So our AST is 315 mm square. So 0.75 times, that is 236 mm square, which is need to provide this location, especially at all the 4 corners. So what is the length we need to calculate? So length over which torsion steel is provided. So 1/5 of shorter span. So 1/5 we have to take this as shorter span is 3500, which is equal to 700 mm. So the length of the torsion steel is provided is 700 mm. Here also 700 mm. Here also 700 mm. So all the 4 corners we need to provide 700 mm of that 236 mm square of steel, which is prevent the lifting. So provide, here we provide for the purpose of lifting only, so we need to provide the 6 mm bar enough. So 6 mm dia bar at 120 mm spacing, center to center support from the length of 700 mm at all the 4 corners in 4 layers to prevent the lifting. So next condition, next step is check for deflection. So we need to compare L by D max, L by D actual. So L by D max is formula is L by D basic into KT into KC, which is already we discussed. So L by D basic for the simply supported beam, slab or beam, we having a value of 20, and KT value we need to refer the based on the FS value, which is provided in the graph. That graph value KT. Page number 38, this graph you need to refer for the FS value. Based upon the FS value, percentage of tensile reinforcement which is touches on the curve FS equal to 240, which is touching on the point 1.6. So KT value is 1.6 into compression reinforcement means conversion factor is 1. So 20 into 1.6, which is value is 32. So actual L by D value is L is 3640, then actual depth is 140, so 26. So actual depth is 26, maximum depth is 32. So L by D max is greater than L by D actual, so deflection is under control. So this is the reinforcement details of two-way slab. So this is the two-way slab reinforcement diagram. This is the cross section. So if you cut X here, it will be look like that. When we see from the cut section, the 4 layers of reinforcement is there. Bottom reinforcement, then perpendicular reinforcement, then one mat foundation, then over the torsion reinforcement. So torsion reinforcement length is 700 mm, that 4 layers of torsion steel. Then this bottom reinforcement is 10 mm, 250 mm center to center spacing. And perpendicular reinforcement 10 mm dia bar, 300 mm spacing. So overall depth is 165 mm. This is the detailed top view of the two-way slab reinforcements diagram. So 0.1 length of that steel provided. Then spacing, when we are look from the top, so this is the reinforcement gap. Spacing is 10 mm, 250 mm center to center. So for this 10 mm dia bar, 300 mm spacing center to center. So this bend also 0.1 times of L. So here torsion steel detail diagram, torsion steel 4 layers of 6 mm to 120 mm center to center spacing. The edge strips as per the condition 560 mm, then middle strips 3375 mm, then edge strips 562 mm along the 3.5 meter direction shorter span. Edge strip is 437 mm, middle strip 2615 mm, edge strip 437 mm. This is the 4.5 longer span, this is the 3.5 meter shorter span. So this is the reinforcement details of two-way slabs. So all the diagram we need to provide detailedly, then only we can easily execute the in the field. Thank you all. I hope everyone will understand the problem related to the two-way slabs. We will see the another video. Thank you all.